Let's take a look at how to interpret the regression output that we get from linear regression. The linear regression output gives us a lot of information. We'll be looking at quite a bit of that information, but not all of it. We'll be looking at what is relevant for our purposes. Okay, so here is our good old bostonhousing.csv file. So we read that file into our data frame called BH, and that's what the data looks like. You've got so many columns. MEDV happens to be the target attribute. All the others are numerical predictor attributes. And for now, we just build a linear regression model for predicting MEDV based on all other attributes. So we use dot. And notice that for the purpose of this exposition, we are not doing any partitioning of the data into training and test. Of course, if we are looking at this data in the context of a predictive analytics exercise, we would definitely partition the data. But for now, just to illustrate the output of linear regression, we are not partitioning the data. Okay, so you can, once you build the linear regression model and store the result in a variable called bh.lm. Once again, the .lm doesn't mean anything. It's just I'm using that to indicate that this variable contains a linear model .lm. It's just a convention, so we follow that. So once we do that, if we do summary and we supply a linear regression model, then you get this typical sort of an output. Now let's learn to interpret all the information that this output contains. So first of all, we've got all of the regression coefficients. Okay, so these are all the estimates for all of the coefficients. Okay, so this is nothing but the intercept is beta 0, this is beta 1, beta 2, beta 3, beta 4, etc., etc. So we've got a number of predictor attributes. I think there are 14 predictor attributes. So you've got so many different coefficients. Okay, and here you see it says residual standard error 4.745. This really happens to be the standard deviation of the residuals. By residuals, what we mean are the differences between the predicted values and the actual values on the data that was used to build the model. So typically you would be doing this on a training partition, and therefore what it's telling you is the predicted values for the training partition minus the actual values for the training partition. That's the error for each of those, for each case. And this is nothing but the standard deviation. Okay. Now you can treat this almost as synonymous with the RMS error. Okay, so this is the standard deviation, not exactly the standard deviation, but it's the standard deviation calculated on something known as certain degrees of freedom. Okay, we are not going to get into that. So for our purposes, we're going to treat this value simply as the RMS error. Okay, for us, this is synonymous with RMS error. Okay, so that's something to be learned from the model. You get all the coefficients and then you get your RMS error. For the most part, we are good to go with those two things really. But of course, there are many other things we need to look at. For example, there are all these coefficients. Which of them are important? Which of them are not important? We'll be looking at all of those things now. Okay, the important point here is that when you do linear regression, there is an implicit assumption that you're running the linear regression on a sample. Okay, it's on a sample and not on the complete data. That's what that is an assumption that is made by linear regression, and quite often that assumption is actually valid, right? Because whenever we gather data, in some sense, it's only a sample. In very rare cases, would you think of the data that is gathered as an actual population? Okay, so given that that is the case, given that it's only a sample, obviously the coefficients we are getting here are only estimates, right? Because let's say that if I had chosen a different sample, then obviously the calculated coefficients would be different. Okay, so what you're seeing here is that these coefficients are only reflective of the specific sample that we have used for this computation. Therefore, what you're seeing here is the standard error, or basically, if you repeated this exercise with many different samples, then obviously each coefficient that you get here would not be the same every time you run it. You'll get different values for the coefficient. right? So for example, the CRIM coefficient, the first time you ran it, you got this coefficient value. Next time you run it, you'll get something different. The next time you run it with a different sample, you'll get something different. Let's say you did this 100 times, then you will get 100 values for this particular coefficient. Okay, and those 100 values will have a certain standard deviation, right, showing the variability. Now, if the variability in those values is very small, okay, then you think that, well, that's good because it's not varying too much. So what I'm able to get is quite a reliable number. On the other hand, if the variability of that value is very high, then you say, well, I don't know. If I get a different sample, I may get a number which is drastically different, and so I cannot rely on it. So that's the significance of that variability. Okay, so you get this because the system is assuming that this is a sample and it's somehow calculating what would be the standard deviation if you repeated this exercise on many samples. So that's what the coefficient is, the standard deviation or the standard error of the coefficients. Okay, so then, so this is what we looked at, standard deviation of the coefficient if repeated on many samples. So for the CRIM, usually we don't worry about that value for the intercept. Okay, we only worry about it for the actual model coefficients, not the intercept. Okay, the coefficients of the attribute. So let's take this attribute called CRIM, and for CRIM, you've got an estimate of minus 1.08 e minus 1. E minus 1 basically says multiplied by 10 raised to the power minus 1, or essentially this is divided by 10. So the actual value is minus 0.1080. That's what it is. Okay, and the standard deviation is 3.286 e minus 2, which means divided by 100, e raised to the power of minus 2, which is 1 by 100. Okay, and that's what this is. Okay, so the basic idea is, well, what if the actual coefficient is 0? In other words, what if in reality CRIM has no effect on the target attribute, but we are seeing a certain effect, this coefficient, only because we picked some crazy sample. Okay, so that's the concern we have here. I got a sample, I did a regression, I got a coefficient. Well, what if in reality there is no connection, but the stupidity of this sample is telling me there's a connection? In other words, this is not a reliable sample, but somehow I managed to get this unreliable sample, and it's now telling me that there's a connection between these two, right? So that's what we want to be sure about, that this is not something crazy that's happening, and that if you repeated it on many samples, you'll still get some value which is somewhat like this. Okay, so the specific question we ask is, what if the real coefficient is 0? In other words, CRIM has no connection, but this sample is just telling us that value. Okay, so that is what this probability is. The fourth column is telling us, well, if the real value is actually 0, then the probability of you getting this coefficient, right, a value different from 0, the probability that you will see such a coefficient as this is this 0.001087. In other words, it's extremely unlikely that you will see this value for the coefficient if the actual coefficient was 0. Okay, so this says, okay, it's very likely that this coefficient is actually different from 0. Okay, this is giving us some confidence that, well, CRIM actually has an effect on MEDV, on the target attribute. It's not something spurious that's happening because of the sample, but it's extremely likely that it really has an effect. That's what this last column is telling us. Okay, and basically what this t value is telling us is, this is the actual coefficient, this is the standard deviation. Okay, and it's telling us if the real value is 0, then how many standard deviations away from 0 is this coefficient? Okay, so clearly you can do that by dividing these two values, right? Because this is the actual value, that's the standard deviation. You divide it and you'll get this particular value. Okay, and of course this is the probability, as we've already discussed. Okay, so this value is really nothing but derived from these two. Okay, so effectively we want to see how likely is it that we'll get such a value if the real value is actually 0. Okay, and you get all these annotations on the very last column. They tell us the level of significance. Okay, so with 3 stars meaning this is highly significant. In other words, the probability of us seeing this coefficient, if the real value was 0, is extremely low. That's what it's telling us. Okay, so you've got blank, which means the probability could be quite high. It's greater than 0.1 that you will see this coefficient even though the real value is 0. So in that case, you will say this coefficient is not significant. There's nothing here. Okay. Otherwise, you have the significance values of dot, 1 star, 2 star, 3 stars. Okay. So the moment you see anything, then it is significant. Okay. But typically we go with a star, not with a dot, right? Because dot says that it could be there is more than a 10% or between a 5 and a 10% chance that the correlation that the coefficient you're seeing is spurious. Okay, and we don't want that. We want much more confidence, right? We want to be at least 95% confident. So we will rely on at least 1 star for the coefficient. Okay, so that's the idea here. So on the right hand side here, we are looking for at least 1 star to reassure us that there is really a relationship. Okay, and these stars are described by the legend shown here, significant codes. Okay, so these are the significance codes, and what this is telling us is if you see 3 stars, okay, then the probability that the coefficient is actually 0 is between 0 and 0.001. Okay, so if that probability is between 0 and 0.001, then you'll see 3 stars. If it's between 0.001 and 0.01, then you'll see 2 stars and so on. Okay, so that is how you interpret what is in the last stars. So dot would mean that it's between 0.05 and 0.1, which is that it's between 95% confident and 90% confidence. Okay, in statistics, it's very common to look for a 95% confidence or more, right? Which is why we are looking for a 1 star, because that says it's 95 to 99. That's what it tells you. Okay, and that's what we are looking for. So now let's take a look at the residuals. So if you do summary bh.lm dollar residuals, then of course you see that the mean of the residuals is always 0. Okay, and that's what you're seeing from your regression output as well. Okay, this is just, I did summary bh.lm dollar residuals. That is, we took all the residuals and found their mean. It turned out to be 0. Okay, and this summary is what you're seeing here too. When you see residuals and it's telling you the summary, most of the numbers match closely, except for this number. It says 595, it says 594 here. I'm not sure exactly where this round off error comes from. Okay, so the sum and the mean of the residuals are always 0. That's a property of linear regression.